Hi everyone, and welcome to our first day of digital classes. Just a quick reminder that there's a problem sheet posted on Google Classroom, and your class participation grade is for you to follow along with the problem sheet and fill that out and submit that on Google Classroom. And then there's some textbook problems that are going to be homework for this lesson. Okay, so let's go ahead and get started. Okay, so I've pulled up a PowerPoint that has a do now here. Go ahead and take a minute to pause the video and answer these questions on your own, right? You'll get a lot more out of this if you actually solve the problems on your own first before we go over them. So go ahead and hit the pause and solve this on your own. Okay, so let's take a look at these problems. This first reaction, we've got two aqueous ionic compounds reacting with each other. That suggests that we're probably going to have a double replacement reaction, right? We're going to end up making sodium chloride and barium sulfate, right? And if you remember the solubility rules that you learned, right, we learned that group 1 ions are always soluble. So we know NaCl is soluble. We also know that for a double replacement reaction to actually happen, one of the products has to be insoluble. So barium sulfate must be insoluble. If we look at the second reaction, right, we're going to make calcium chloride, and then H is going to combine with OH to make water. Okay, there's our net ionic equation for the first one, right? And for the second one, we should go ahead and balance this. Oh, the first equation is not quite balanced. There should be a 2 in front of NaCl. For the second equation, we can see that our net ionic equation, right, is the reaction of H plus and OH minus binding together to make liquid water, right? In the first reaction, barium and sulfate bound together to make barium sulfate, right? And sodium and chloride were just spectators, right? Nothing actually happens to them. In the second reaction, calcium and chloride are just spectators. The way it's written, it looks like calcium and chloride are bonding together, but they're really not. They're both just floating around in the solution the entire time. Right, so there's our net ionic equation. For the third reaction, we're going to form potassium fluoride and magnesium phosphate. And again, group 1 ions are always soluble, so magnesium phosphate must be insoluble, right? And the potassium and the fluoride don't actually form a bond in the products, right? They're both just separate ions floating through the solution. So the net ionic equation is forming magnesium phosphate. And make sure that you've written the correct formula for magnesium phosphate, right? You have to use the crisscross rule to make sure the charges are balanced. So we've got Mg2 plus and PO4 3 minus. If you crisscross those charges, Mg3, PO4 2. Good, so that formation, that's our net ionic equation. I guess we should balance the original equation first, and then there's our net ionic equation. For number 4, we're gonna form sodium chloride and copper hydroxide. Again, sodium chloride's soluble, so the other one must be insoluble. We can go ahead and balance that. And then our net ionic equation is forming the solid. There we go. Oh, that came out of order. Whoops. And then for number 5, good, we've got calcium nitrate and lead to bromide. Right, there's our net ionic equation. Cool. So you'll notice that we've talked in the past about solubility and things that are soluble and insoluble, right? Sodium chloride is soluble, barium sulfate is insoluble. Calcium nitrate is soluble, lead bromide is insoluble, right? And we've always talked about solubility as being a binary. Something's either soluble or it's insoluble. Well, that's actually a little bit misleading. No substance is ever truly insoluble. When we say that something's insoluble, what we really mean is that it has a very low solubility. There you go, right? It's got a very low solubility. Nothing is ever actually 100% insoluble. And so that's important to think about. Something that is supposedly insoluble really is just a very low solubility. So a very, very, very tiny amount of it will dissolve into water, and the rest will just stay undissolved. And so basically anytime you try to make a solution of one of those substances, for example, anytime we try to make a solution of, lead bromide, which is allegedly insoluble, right? As soon as you try to dissolve some, the maximum amount will basically immediately dissolve, and you'll pretty much always end up with a saturated solution. So insoluble compounds are pretty much always forming saturated solutions because their solubility is just so low. And we've talked in the past about how saturated solutions are actually in equilibrium, right? So in a saturated solution, for example, if we had a saturated silver chloride solution, right, the rate of the solid dissolving into the solution is equal to the rate of the two ions coming together and recrystallizing to form the solid, right? So we've got an equilibrium. Take a minute to write down the equilibrium constant for this equation, right? KEQ. You should actually be writing it down. Cool, so this is a heterogeneous equilibrium, meaning there's two different phases. And if you'll recall, solids do not affect the equilibrium constant, so we would write the equilibrium constant like this. It's just Ag plus concentration times Cl minus concentration. And this is an equilibrium constant, but it's specifically referring to the dissolution of this compound, AgCl. And so we have another name for this. We also call it the solubility product or solubility product constant, which we abbreviate with KSP because, you know, we need as many different possible Ks as we can possibly come up with. Cool. It's important to realize that the solubility product constant and solubility itself are not the same thing, right? So solubility products are not the same as actual solubility. Solubility products are only listed for substances that are essentially insoluble. Right? A substance that is soluble would have a very, very, very high solubility product, and we just don't bother listing it. Solubility products refer to saturated solutions, right? Like all equilibrium constants, we don't put units on them, right? Technically, it would be like either molars squared, molars cubed, molars to the fourth, whatever. But in reality, we just never write units for equilibrium constants. And then KSP is not the same as solubility. So here's some example KSP values, which you can see kind of vary, but they're all quite small. Right. Solubility, to clarify, is the amount of salt that dissolves in a given amount of solvent to give a saturated solution, right? So solubility is often measured in like grams of solute per liter of water or grams of solute per 100 grams of water. Sometimes it's just measured in like moles of solute per liter of water, right? But it's always the amount of solute per the amount of solvent, right? So units would be either grams per liter, moles per liter. You know, you can do like grams per 100 grams or grams per million grams as well. Solubility product is an equilibrium constant. And so the solubility product is the product of the concentrations of the ions. And it has no units. So solubility and solubility product are related, right? If something's more soluble, it's going to have a higher solubility and a higher solubility product. If something's less soluble, they'll both be lower, but the numbers are not equal. So we're going to look today at converting between those two numbers. But before we do that, let's quickly write the KSP expression for these three different saturated solutions. So again, pause the video, take a minute to actually answer this, right? Do it yourself, then we'll go over it. Okay, so for the first one, right, our KSP is just the product of the barium ion times the chromate ion. For the second one, right, this compound's going to break apart into 3 ions, 2 silver ions and 1 chromate ion. So our KSP is the concentration of silver squared times the concentration of chromate. And for the third one, we get concentration of silver cubed times the concentration of phosphate. Cool. So we're going to talk about calculating molar solubility from a KSP value. So let's look at this example problem, right? So they give us the KSP value of calcium fluoride, and they're asking us for the molar solubility, right? The moles per liter of calcium fluoride that can dissolve in water. We can calculate this using what we know about equilibrium, right? If we have KSP, we can calculate the concentrations of the different substances at equilibrium, right? Let's go ahead and write an equilibrium equation for what's going on, right? Calcium fluoride is dissolving to make one calcium ion and two fluoride ions. And then anytime you have equilibrium, it's helpful to write an ice table. So let's go ahead and do that as well, right? So here's our ice table, right? And this KSP value is essentially representing the equilibrium as calcium fluoride dissolves into water. And so we can think about it as, okay, we're going to dump a bunch of solid calcium fluoride into a solution, and then that's going to reach equilibrium eventually, right? Now, the amount of calcium fluoride that we dump in has no effect on the equilibrium, right? Calcium fluoride is a solid, so it doesn't affect equilibrium, right? If you have a saturated solution, that's the only way you get equilibrium is a saturated solution. If you have a saturated solution and you dump in more calcium fluoride, it's not going to dissolve anymore, right? If you remove some of the calcium fluoride, it's not going to dissolve any less, right? So the amount of calcium fluoride that we put in, as long as it's enough to reach equilibrium, which it definitely will be since this K value is so small, right? As long as it's enough to reach equilibrium, the amount of the solid doesn't matter. It has no effect on equilibrium. So that's why we're not given that information in the problem. It just doesn't matter. And we can assume the other two ions start with 0 concentration, right? As calcium fluoride dissolves, right? As the reaction proceeds, some of this is going to dissolve, so the amount of calcium fluoride will go down, right? The amount of calcium ions will go up by the same amount. And then for every 1 mole of calcium fluoride, we get 2 moles of fluoride ions. And so that would be plus 2x. And again, the amount of calcium fluoride at equilibrium is irrelevant because it's a solid, but the amount of calcium ions is x, oh hi, and the amount of fluoride ions is 2x. This is my cat, Hera. Say hi. There she is. Okay, moving on. Cool. So we can write out our equilibrium KSP, right? And we can go ahead and plug in the values that we have, right? So we know that for calcium, that's going to be x. For fluoride, that's going to be 2x. The concentration of fluoride is twice the concentration of calcium, and it's squared in our equilibrium expression, right? So that 2 in this chemical equation is like affecting this problem in 2 different ways, right? This 2 is affecting the power of the fluoride ion, and it's also affecting the concentration of fluoride. So we end up with KSP equals 4x cubed, right? From multiplying x for calcium and 2x squared for fluoride. We know what KSP is, we're given that in the problem, and so we can go ahead and solve for x, right? So we've got 4x cubed equals 3.9 times 10 to the negative 11. You solve that for x, you get 2.1 times 10 to the 4th molar, right? That's the amount of calcium 2+, the concentration of calcium 2+ ions at equilibrium, right? The concentration of fluoride ions would be twice that, right? So 4.2 times 10 to the negative 4. And of course, the question was actually asking us for the solubility of calcium fluoride, right? So essentially the moles per liter of this that dissolved. Well, the moles per liter of this that dissolved is the same as the moles per liter of calcium 2+, right? So it's just 2.1 times 10 to the negative 4th moles per liter. That's the answer. Cool. We can also go back the other way, right? If we know a molar solubility, we can calculate KSP from that. That's actually, I think, a little bit easier. So for example, we're given this question, we're given that the solubility of calcium sulfate in water is 0.67 grams per liter, and they're asking us to calculate the KSP value. It's always helpful to write the actual chemical equation that's happening. So in this problem, that's this, right? Calcium sulfate is dissolving to make Ca2+ and SO4 2-. And then we need to we do everything in terms of where all of our equilibrium concentrations, KSP, is in terms of molarity. So you're going to have to convert grams per liter to moles per liter in order to be able to use that number to calculate KSP. So that's easy, right? We know the molar mass. You can go ahead and calculate it. It's 136 grams per mole of the molar mass of calcium sulfate, right? So then you can go ahead and convert 0.67 grams per liter times 1 mole per 136 grams. Grams cancels out. You get the concentration or the solubility in moles per liter. And then from that, we can calculate KSP. And it's worth recognizing, for every mole of calcium sulfate that dissolves, you get 1 mole of Ca2 plus and 1 mole of SO42 minus. Right? So when we're calculating KSP, we're multiplying together those concentrations. Both of these concentrations are just equal to the original concentration of calcium sulfate that dissolved. Right? So we just have 4.9 times 10 to the negative 3 squared. And so we get 2.4 times 10 to the negative 5. Cool. And remember, KSP has no units. Good. Go ahead and take a few minutes to answer these example problems here. You can either answer all of them at once and then check back in, or answer the first one and then we'll go over it, and then pause the video again, answer the second one, we'll go over it. Do it either way, whichever you prefer. But make sure you solve it on your own first before you watch us going over it. That's the only way to really learn it, is to solve it on your own first. If you get stuck, come in and watch just until you have enough of a start to get you started on the problem. Pause it again and finish the problem on your own. Right? The more you're working through these problems on your own, the more you're really going to learn the material. Yeah. Good. Okay, so let's look at this first one. We're looking for the KSP for copper 1 bromide. It would help if we knew the formula, right? That's CuPr. And then in order to calculate the KSP, they've given us the solubility. Conveniently, this time they give in moles per liter, so we don't need to convert from moles per liter to grams per liter. It helps if you write the chemical equation for what's happening. And then you need to relate the solubility to the concentrations of each of the ions. In this equation, it's all 1 to 1, right? So this concentration is also going to be the concentration of Cu plus and of Br minus. We can write our equilibrium product or our solubility product, right? That's just the concentration of Cu plus times the concentration of Br minus. There's no coefficients, so we don't have any powers in our KSP expression. And then we just plug in 2.0 times 10 to the negative 4 squared, and we get 4 times 10 to the negative 8. Good. If you haven't already solved problem 2, pause and solve problem 2. If you have, let's go over problem 2. Right, so we're looking for the KSP of silver chromate. Here's the expression for silver chromate dissolving into solution. Here's our KSP expression, right? The silver ion is getting squared, and then that 2 is going to show up again, because also if the solubility of silver chromate is 6.7 times 10 to the negative 5 moles per liter, well, for every mole of silver chromate that dissolves, we get 2 moles of silver ions. And so the concentration of silver ions, right, is going to be twice the concentration of the dissolved silver chromate, right? So 1.34 times 10 to the negative 4 molar. I'm not rounding, because I want to get my final answer before I round anything. Good. Okay, so our KSP, we can plug in the 2 concentrations, right? The concentration of chromate is just the same as the concentration of the original silver chromate ion, because they're a 1-to-1 ratio. So I'm plugging in this doubled concentration of silver, and then that also gets squared, and then that gets multiplied times the concentration of chromate, and that should give you 1.2 times 10 to the negative 12. Good. Go ahead and take a minute to answer the next 2 problems.
Okay, for the last couple problems, I'm doing this on paper because doing math in PowerPoint is like a pain in the neck. Okay, so problem 3, right? We are given the KEQ for lead 2 iodide dissolving, and we're looking for the molar solubility. So I would start by just writing in the equation for what's happening. I'm leaving out the states because I'm lazy, right? But this would be solid, and then it's dissolving into aqueous ions. And then anytime you have equilibrium, it's always nice to make an ice table. The amount of solid lead iodide that we start with is irrelevant. So I'm just going to put like a little line there, right? And we'll assume we start with none of the other two. And then what's happening is that some of the lead iodide is dissolving into ions, right? And it's worth noting, right, for every 1 mole of lead iodide that dissolves, we get 2 I- ions, 2 iodide ions, right? Okay, this we still don't know, but at equilibrium, we're going to have X lead ions and 2X iodide ions. Cool. We can actually go ahead and relate these values to our KEQ value, right? In the problem, they tell us that KEQ is, 9.8 times 10 to the negative 9, but then also that KEQ value is going to equal, based on this equation, the concentration of lead ions times the concentration of I- ions squared, because there's a coefficient of 2, right? And that coefficient becomes the power in this equation. So that means KEQ is going to equal, well, at equilibrium, the concentration of lead is X, the concentration of I- is 2X, and of course that concentration is getting squared, so we've got X times 2X squared, so 4X cubed, right? And so if you solve for X, right, X is going to be 9.8 times 10 to the negative 9, right? And to reverse this, right, you divide by 4, and then you would take the cube root of this, right? And you can go ahead and plug this into a calculator, right? I already did that, and I got 0.0013 molar. And that's the concentration of lead ions at equilibrium. The concentration of iodide ions would be twice that. The question was asking us for the molar solubility of lead iodide, which is this X value, right? It's the moles per liter of lead iodide that dissolves. Let's go ahead and look at the next problem. Right, so the next problem was kind of similar, but it was asking about silver chloride instead, which is actually a little bit easier because silver chloride is in a 1-to-1 ratio. So when that dissolves, we're going to get Ag plus Cl minus, 1 ion of each for every mole of AgCl that dissolves. So our ice table is pretty simple, right? We don't actually care about silver chloride. We're starting with none of these, but for every mole of this that dissolves, we get 1 mole each of silver and chloride. So we end up with just X and X for each of them. For this equation, right, KEQ would be the concentration of silver ions times the concentration of chloride ions. They're both X, so that's just X times X, so that's X squared. And then we're given the numerical value in the problem, right? It's 1.8 times 10 to the negative 10 equals X squared. So just square root that, and you get X equals 0.000013 molar. And this is the moles per liter of silver chloride that dissolves. So that's our molar concentration.
All right, everyone, I hope you had a great lesson. Let me know if you have any questions, of course. Go ahead and get started on the homework. Let me know if you have any questions about that, and I will see you next time.